Hello. I'd like to talk about the exponential family today. Um, I know it has been covered in many other videos, but I just like to give a different perspective. In the sense that I think many other videos just take it as a very useful tool for Bayesian inference and look at that in that in that way. Um, I like to argue here that it's actually more fundamental than that, and it kind of comes naturally if we consider the following. Let's say we have some random variable x that we don't have complete knowledge of the random variable. I mean, in the sense that we don't have all the statistics, we don't know the distribution of x, but we have some partial knowledge about x. More precisely, we know there's some expected oscillation of x. So the oscillation will be like with some function ti here. So we know the expectation of tix for different I. Let's say for I is equal to 1 up to some value m, let's say. And the question to ask is like, given this constraint, what's the most probable distribution of x? Or maybe I shouldn't say probable, but the most natural distribution of x. So by second law of thermodynamics, we kind of expect that if we just leave a distribution alone for a long period of time, and if we can, the distribution is going to decay itself somehow, or degenerate, or like evolves, or I guess a better word for that, if the distribution is allowed to evolve, and still if we keep that constraint that we have, then essentially the entropy should increase, and so therefore one good argument, or like good candidate of the distribution will be just the distribution with the maximum entropy. And if we assume the random variable is continuous, then we should consider the differential entropy, this script x here, and it's basically given by the expression like that, px log px dx. So I have a minus sign here. Px is basically the PDF of x. So we can use Lagrange multiplier trying to maximize that. But of course, if we maximize HP, we need to insert all the constraints into that. So we have several constraints. First of all, of course, is the knowledge we have about the expected value of ti, function of ti on x. So we can insert that, and for each of these known expectation, we have a new Lagrange multiplier here for that, like eta I. And we also need to make sure that because px is the PDF, so it has to normalize to 1, so we have this integral into of px is equal to 1, and also like for each of the px has to be bigger than equal to 0 for any x. So therefore we have also this last constraint here. Okay, now then we need to be careful that like we're trying to maximize this thing, and we are actually maximizing a function of a function, so it's really a functional. But we don't need to worry too much about that. We can think of like, okay, px can think of px is for one particular component, say for one x. We can think of like this essentially like, for example, I guess it's easier to think of px when x is discrete. Then let's say if x has like is discrete, just take like from 1 to 10. So we have px is something from p1 to p10, right? So what we're doing here is like trying to find the vector here. So for different p here, from p1 p1 and p10 here, p1 up to p10 here, to maximize this function here. So just things become complicated, a little bit more complex when we have x is continuous. Then we really trying to find this px become like an infinite dimensional vector. It's not even infinite, uncountably infinite. It's uncountably infinite. But anyway, we can just like in the vector case, if we are trying to find what's the maximum of this, like in the vector case, we're just trying to take the derivative over some px, right? So essentially, even for the continuous case, we can still do the same thing. So we're trying to, for some x pi here, let's say we're trying to take the partial derivative of this whole thing here, we call it LP here, with respect to this px pi here. So let's just look at one of these terms, like easier to explain. Let's look at the last term here. So if we take the partial derivative of this thing with respect to px pi, there's one px pi here where we take an integral over everywhere. So we have one px pi is the same as that one here, and we take the integral, take the derivative with respect to that point there. We basically get a delta function of x minus x pi, right? So therefore, if we take an integral there, we will get h tilde x pi there. So similarly, we will get the other. I mean, if you trust my math, we will get the rest of the expression like that. And then since we are going to find the maximum value, the extremum value there, we can just set it to 0, set the partial derivative to 0. Then we can rearrange the term, basically move this log px to the other side, and then take the exponential on both sides. Then rearranging the term, eventually we'll get this. And know that, like, because this px here is the probability distribution, and this whole thing is supposed to normalize to 1, and apparently this thing is basically just normalization factor here, and this normalization factor actually depends on eta. Therefore, like, we will just write this term as a eta here, and then this basically will get us the very kind of familiar, I'm not sure familiar or not, form for exponential family, and this is actually the so-called canonical form of that exponential family.